get started in just a sec. Again, if you have questions, you could type it there in the chat box. All right, we're going to pick up with the end of, actually, it's chapter 4. We were talking about naming some covalent guys. Again, these guys are sometimes referred to as type 3 compounds. And again, this is really from chapter 4, just kind of continuing with this handout. And I think we got through sort of how to name them, but just to review, when we talk about type 3 compounds are a certain type of compound. They're essentially when we get two nonmetals together. So they're covalent compounds. Are molecular compounds. So these are guys that will basically share electrons. So unlike our type 1 and type 2, which is a metal and a non-metal, which is an ionic compound, here with type 3, we got covalent bonding, sharing of electrons that hold those guys together. So this is the only place really where we actually do use subscripts. So as we talked about last time, a lot of times people want to always use sort of, subscripts, use prefixes when they go to name things. And this is actually the case where you should use prefixes. So again, we use the prefixes like you see on the screen there: mono for 1, di for 2, tri for 3, tetra for 4, penta for 5, hexa for 6, hepta for 7, and octa for 8. Nona and deca would be 9 and 10. Now, when we do use these prefixes, a couple of things that we talked about there at the end. The first thing is we do not use mono on the first name. But it's okay on the second. So if you just have one of something, you wouldn't use mono on that first name. But if you did have just one of something on the second element, you would use mono, so that's okay. And the other thing that we talked about is a lot of times when you do use a prefix and you do use the first letter of the first element or second element, you'll run into two vowels that sort of back up to each other. So it's very common to get rid of the first vowel on the prefix. To say if this was mono, we would get rid of that first O there on the prefix and then use the second there, which would come from something perhaps like oxide. So instead of monoxide, it becomes monoxide. Also, a lot of times you'll sometimes get an A and an O that will back up. So for example, if this was oxygen, you had tetra. Again, we would get rid of the A in that case off of the prefix. So those are some common things that happen. Two I's in a row seem to be okay. So if you got two I's, you're okay in a row. When we do name these guys, we pretty much will use the whole name of the first guy, first element. And we would use the prefix here as well in front of it, again, as long as it's not mono. And then for the second one, we would name it just like we did with type 1, type 2. We would take the non-metal name. We would drop the last part and put IDE on it. And then also we would use our prefix there to to indicate how many we have. So the prefix as well. And again, here we can use mono on that second one, but not the first one. Any questions on that? Now, as I might have mentioned last time, these are the really the easiest ones to name, to write the formula for, but they are the ones that people mess up the most because they want to always try to do something like balance charges, do all these type of things. Essentially, all you have to do is count how many of everybody you got, pick the right prefix, and then you can basically write the name or the formula, whatever you may be doing. So again, these are a couple of those things that we just talked about in terms of just some things that sort of occur when we're doing these guys with prefixes. So as I mentioned before here, again, if you take the A off of the prefix and then the next letter of the element is an O, we typically will get rid of the A that's there. And again, you get a couple O's that back up to each other. We also would get rid of the O there on the first one to give us sort of the proper spelling so we don't get too many vowels that back up. A reminder that some things do have common names. So we talked about some of them before, but here, this is the most common one, right? Water is H2O. Again, you don't need to call it something like dihydrogen monoxide. Again, should just be H2O, which is water. Trick question. NH3 is ammonia. Again, also not like nitrogen trihydride or anything like that. So ammonia is the correct name for that. Again, not to be confused with that polyatomic ion that we saw earlier, which looks like NH4 plus. Yeah. And again, this is ammonium. So this guy and these two guys get confused a lot. People always mix them up. Again, here, this is an ion. This is not an ion, so no charge on this one. And again, has just the name ammonia. Any questions on that? Okay. So I think you have a few examples here. Why don't you take a moment and work out the names of those, and then we'll talk about what they are in just a second. Okay, so let's take a look at these. So first thing, when you see something like this, you want to look at it and you see I, which is a non-metal. We see O, which is a non-metal. So really, in this case, all you have to do is essentially pick the right prefixes and then put them together. So we have two. They, the previous recording should be there. I'll double check, but they should be in the module sections. Saw them yesterday, but I'll double check. So if we look at the I, it is two of them. So the prefix is di. 7 is hepta. And again, we want to put those together. So again, we're just going to take the full name of the first guy. So this is going to be diiodine. And again, in this case, the two I's together should be okay. And then we have hepta and oxygen becomes oxide. And again, the IDE at the end, just like normal. And we do want to apply our prefix. And we would go like that again, dropping that E there so we don't get the A and the O. That's basically backed up together. Any questions on that? Coming down here, same idea. We look at C, which is carbon, which is a non-metal, O, which is oxygen, which is a non-metal. Again, we only have one of these guys, so the prefix would be mono. Here we have our two, so the prefix would be di. Again, on the first name, we don't use mono, so we would just use the whole name there. And this would be carbon. And then this would be dioxide. Again, the second guy getting the IDE, first guy whole name. And again, no prefix on the first one because it was mono. And lastly, here we see P, which is phosphorus. We see Cl, which is chlorine. Again, both non-metals. We again have only one of these guys, which is mono. We have three of these guys, which is tri. And again, not going to hit the wrong button there. Come back. There we go. Not going to use the mono there on the first one. So we will use the whole name, which is phosphorus. And then tri. And then chlorine will become chloride like the end there. Any questions on any three of those names? Now, when we have type 3, like I said, they really are sort of the easiest. They should be the ones that you should be able to name or write the formulas the fastest. So, for example, if we come over here and we had something like carbon tetrachloride, we had something like dinitrogen pentoxide. Why don't you take a second there and write the formulas for those two? Okay, so like I said, these really should take you probably like 10 seconds to write the formula. And the reason is because once you see these names, although we don't see any prefix here, we do see a prefix here, and that should automatically tell you that it is type 3, which means you don't have to worry about balancing charges. You don't have to worry about anything else other than just writing the actual formula. So when we see a name here with no formula, that implies that there's only one of them. And that means that we would just write C for carbon. And tetra is a prefix for 4. And chloride is Cl, so that would be Cl, and you put the 4 on the bottom. Again, the nice thing about these, you don't have to worry about balancing charges. There's no charges involved or anything like that. So it's just simply write what the formula basically says or the name says. Same thing here. We see di and we see penta. Again, both prefixes tells us we just need to write what it says. So di is 2 and nitrogen is N, so it would be N2. Penta is 5, and oxygen, our oxide is oxygen. Then we write O5, and that would be it. So I think these are, again, the sort of easiest to name and also write the formula. But I will say these are the ones that most people, or a lot of people, really sort of screw up by trying to do all kinds of weird things like balancing charges and those type of things. Any questions on how to name type 3 compounds, which again in your book I think is out of chapter 4. So that should conclude how to name pretty much everything. We talked about naming type 1, we talked about naming type 2, we talked about polyatomic ions, we talked about acids, and we now talked about type 3, and that should cover pretty much all the naming that you have to sort of do. So just a quick review of those. Again, type 1 is a metal, non-metal, and we use the whole name of the metal, and the non-metal gets the IDE at the end of it. And it's always the metal that's important there. Excuse me. When we name those guys, and the metal in type 1 would be group 1, group 2, and group 3 are zinc, cadmium, or silver. And that's very similar to type 2, which is also a metal and a non-metal. Also, the metals important there will be a transition metal. And again, we use the whole name. This is where we use those Roman numerals. And then the non-metal with the IDE at the end of it. And type 3, as we just talked about, 2 non-metals with our prefixes. And again, so prefix in our first name, the whole name, and prefix for our second name that gets the IDE at it. So none of these switch over. So this guy, type 1, no Roman numerals, no prefixes. Type 2 should have Roman numerals, no prefixes. And type 3 is the one where we use our prefixes. So if you find yourself using a prefix and a Roman numeral together, you should just mark it wrong yourself, because it is going to be wrong. Yeah, so they never are together. You only use them separately in each of these situations. Any questions on any type of naming or anything like that? Okay, so then we're going to continue actually with chapter 4, but we're going to switch to the next handout that you got there. So give me a second here to get that up. Try that there. 1 second here. There we go. All right, let's try that. And maybe. Okay. All right, here. Sorry, hang on here. Just doesn't like what I'm trying to do. Let's see here. Do that. There we go. That one I liked. Click the right button. All right, try that again. There we go. All right. So again, this really is a continuation of chapter 4, which we were using before. All right. So hopefully you can see that there on the screen. Okay. So in chapter 4 here, we're going to continue and we're going to talk about bonding now. And we're going to talk about bonding in a couple different ways. We're going to talk really about covalent bonding. In the previous chapter, in chapter 3, we talked about ionic bonding. And we are again going to use Lewis symbols and Lewis dot symbols to help us do this. Again, remember that Lewis dot symbols are basically the symbol plus a dot to represent a valence electron. And remember, no more than 2 dots per side for a grand total of 8 valence electrons. When we think about valence electrons, we can figure it out from the group number. So the number of valence electrons equals the group number. So again, everybody in group 1 has 1, everybody in 2 has 2, and so forth as you continue down your periodic table there. And again, you could also write the electron configuration, but this is obviously a much easier and faster way to figure out, how many valence electrons something has. So when we talk about chemical bonding, we're going to talk about a covalent bond. And again, this is different than an ionic bond that we've seen or talked about in the previous chapter. Here, we're going to talk about a covalent bond, which is the sharing of electrons. And the sharing of electrons happens when we look at something, say, like hydrogen here. These 2 electrons are going to actually be shared between them. And in this case, that represents a covalent bond. So when we do have a covalent bond, like something like hydrogen, we could represent it one of 2 ways. We could represent it with the 2 dots that are being shown between the 2 atoms. Again, 1 dot from each hydrogen, as it has 1 valence electron. So its Lewis dot symbol, right, would look like that. And what is nice about this is when we look at those electrons in the middle there do count for both of the hydrogens. So for example, if we come over here, those 2 will count for the hydrogen on the left. And if we come over here, those 2 will count for the hydrogen on the right. So in essence, they are both sharing 2 electrons, and that gives them both 2 electrons in this case, which is good. And that's good because if you look on the periodic table, You got hydrogen, and then the next element after hydrogen is helium, which is a noble gas. And remember, the whole purpose of all kinds of bonding, both ionic bonding and covalent bonding, is for everybody to kind of get to the same electron configuration as the noble gases. I'm just going to put this back up in 1 second here. That will fix it, hopefully. Okay. And the purpose of bonding, both ionic bonding and covalent bonding, is for everybody to get to that noble gas configuration. I want up there it is. Okay. And in the case of hydrogen, again, only needs to get to helium in order to get to that noble gas, and it's perfectly fine, which means it only needs to get to those 2 electrons, which means hydrogen, one important role bonding is hydrogen essentially will only need 2 electrons. And that's important for hydrogen because that means when hydrogen is in a bond, back here, sorry about that, technical difficulties here. There we go. When hydrogen is in a bond, it should always be on the outside. So it will always look something like this. Or if you decide to draw it with the dots, it will look like this. You'll never have hydrogen in the center, because if hydrogen was in the center, bound to anything else, it would obviously have more than 2 bonds. So hydrogen always has to go on the outside, never in the center. But you can represent the bond like we do here with the dots in between. You could also represent the bond as it shows there on the bottom with a line to represent that bond that's happening between those 2 elements. Again, means the same thing. It means that they are sharing a pair of electrons. And this is what is referred to as, we'll see, a single bond. Again, a single bond is represented by 2 dots, which is a pair of electrons, or you can represent it by 1 line, basically. And again, you can use it either way. You can use the dots or you can use the lines. I personally will probably represent the bonding by using lines, but you could use dots if you wanted to, as we will see as well. You could represent a double bond with basically 2 pairs of electrons or 4 electrons, or you can use 2 lines to represent a double bond between 2 elements. And as we'll also see, a triple bond can be represented the same way. You could use dots, which in this case would be 6 electrons or 3 pairs, or you could use the 3 lines that represent a triple bond. So here again, in covalent bonding, the difference between that and ionic bonding that we talked about in the previous chapter. Again, ionic bonding, there is absolutely no sharing of electrons. They have been transferred from the metal to the non-metal. But here in covalent bonding, we do have sharing of these electrons. Any questions on that there? And it is that attraction between the 2 nucleuses that basically will hold that bond together. So again, if you think about it, if you had, say, atom A here and atom B, and kind of a long bond there, but our electrons here in the middle, they're being shared, is going to feel some attraction to the nucleus, right? Because he's got a positive nucleus, he's got a positive nucleus. So it's going to feel some attractions to the nucleus of A, but it will also feel some attraction to the nucleus there of B. And again, it's that kind of attraction to both of those nucleuses that essentially will kind of lock those electrons into place between the 2 atoms. and they will be shared. And as we'll talk about in this chapter, sometimes that sharing is, perfectly good and kind of equal, and sometimes that sharing is unequal. And as we will see, that leads to two types of covalent bonds. One which is known as a nonpolar covalent bond, and that is equal sharing of electrons. So in that case, these electrons are going to be shared equally between the two atoms. And then we'll see a polar covalent bond, which is basically unequal sharing of those electrons. And that means, as we will see, maybe in this situation, the electrons kind of hang out a little bit more towards, say, the right-hand side there than the left-hand side, and that creates a different type. So unlike an ionic bond where you pretty much just have one type of ionic bond, which results from those electrons being transferred from the metal to the non-metal, in a covalent bond, you actually can end up with one of two types of covalent bonds, and it's all depending on how those electrons are actually being shared between those two atoms. Any questions on that? So for example, if we look at F2, fluorine, which is group number 7. And what that means, again, a reminder that if you go to the periodic table, group 7 means that fluorine, again, would start like we see on the bottom there with 7 valence electrons. And the other fluorine would also start with 7 valence electrons. And when we look at this, what's going to happen in this case, because they are both nonmetals, they're actually going to end up sharing electrons. And that's because they're pretty much in the exact same location, obviously, on the periodic table. But when two nonmetals come together, and we look at two nonmetals, and I think we talked about some periodic trends. Again, nonmetals up here in this region, they all have very similar properties, our periodic trends. And those similar properties basically means when we get those two nonmetals that come together, a nonmetal and a nonmetal, essentially neither one of them wants to give up their electrons. So that the best that they could do is they decide, well, I don't want to give up my electron. I don't either want to give up my electron. So what ends up happening is they sort of compromise, if you want to think about it that way. They compromise and decide, all right, well, I'll share my electrons with you. And that's very different than what happens in an ionic bond, as we talked about in the previous chapter. Again, an ionic bond is a combination of metals, which are this part of the periodic table, and our nonmetals over here. And when we get those metals and nonmetals together, the difference in sort of their periodic trends is, if you remember, metals are like, I don't really want to hang on to my electrons. Here, you take my electron. So you get that transfer of electrons in an ionic bond. So this is our covalent, which is what we're talking about here in this chapter here. So that's why there is some aspect of sharing when we do get two nonmetals together, because they do have very, very similar periodic trends, and nonmetals typically want to hang on to their electrons, so they will share them rather than getting that sort of transfer of electrons like we do see in the ionic bond. But the end result here is the same. If we look at the fluorine here, those two electrons are being shared for both of the fluorines. So the guy on the left, if we look at it, has 2, 4, 6, 8 electrons. So he ends up with 8 electrons. The guy on the right here, also going to use those 2 electrons in the middle to share, will also end up with 2, 4, 6, and 8 electrons. And again, if you remember on our periodic table, right there at the very end, group number 8 is our noble gases. Yeah. So in this case, the way they're able to achieve that noble gas configuration, if you want to think about it that way, is they actually are able to do that by sharing these electrons. as opposed to in a ionic compound like we talked about in the previous chapter. The way they're able to get to that noble gas configuration is by transferring electrons. But here in a covalent one, we're going to be sharing those electrons. Any questions on that there? And again, like we see on the bottom here, you can represent the bond between the two F's with the dots like we did here. Or again, instead of the dots, you can use, a line to represent those electrons that are being shared. And when we look at this sort of structure here, we see a couple of different types of electrons that are involved. So where all the big claws came in over here, all these guys here, which are not involved in any type of bond. And they're not involved in a bond because there's no element symbol written on the other side. So they're just kind of dots. These guys are sometimes called lone pairs. And I'll oftentimes call them lone pairs. But nowadays, most people and most textbooks will call them non-bonding electrons. Very fancy name there, non-bonding electrons, which much like the name implies, they are not involved in any type of bonding. So these are non-bonding electrons. And again, or you could call them lone pairs as well. So that's another sort of name for it that means the same thing. It means basically electrons that are not involved in any type of bond are those non-bonding electrons. You should always include the non-bonding electrons when you draw these Lewis structures. So you should always make sure they're part of it. And then obviously these bonds right here are these electrons right here. They also have a name. And since those electrons are involved in a bond, they also have a very creative name. They are known as bonding electrons. So these names are pretty self-explanatory. If you have bonding electrons, that means those electrons are involved in some type of bond. As we can see there in the picture, those are the electrons that are actually between the two elements, the two F's. And our dots there that we draw on these Lewis structures are what are referred to as non-bonding electrons, or sometimes called lone pairs. And those are the electrons that are not involved in any type of bonding. As we can see, we don't see them on there's no other element on the other side of them. Question on bonding electrons, non-bonding electrons. Again, obviously, as we're going to talk about how to draw these things in a second, but you do want to make sure that you always put all those types of electrons in when you draw these Lewis structures, which is what these are called. So a Lewis structure, as I mentioned, is pretty much what we had drawn there on the last page. It is basically a structure that we use the symbols, and we use dots or lines there to represent electrons that are being shared in a bond. And we use pairs of dots to represent non-bonding electrons, which are not involved in bonding. It is important to remember that only the valence electrons are shown in Lewis structures. So each of these elements have a lot more electrons. But just the valence ones are shown there in the bond in the Lewis structure. So if we look at water, for example, and we draw the Lewis structure there for water, again, going through the steps to draw the Lewis structure, which we'll talk about later, you will end up with one or two pictures here. This picture is basically just using dots to represent both bonding and non-bonding electrons. This one over here is using a combination of dots and lines. The lines would represent our bonding electrons. The dots here would represent our non-bonding electrons. And those would be non-bonding. And again, these guys over here would be our bonding electrons. So when we do this, what we see happens again through sharing of electrons. Remember that hydrogen is actually a nonmetal, so it's going to want to share electrons in this situation. As we can see below, by sharing the electrons, the hydrogen on both sides again are able to get to 2 electrons. And as I drew up on the other slide, that's enough to get hydrogen to get over to helium and become just like helium in a sense in terms of electrons and be very stable. And then our oxygen will end up sharing 2, 4, 6, 8 electrons, again allowing oxygen to move forward to the noble gas as well, and ends up having 8 valence electrons around it, which makes it really, really stable. And again, that's just, again, the purpose of any type of bonding, as we've been talking about. The goal there is to get to that noble gas configuration. Again, because if you remember, noble gases are, they're chemically inert, which means they don't combine with other things. They're very stable just the way they are. So everybody's trying to achieve that through bonding. And the way, again, we do that in covalent bonding is to share electrons. So definitely for covalent bonding, that brings up 2 really important rules that you need to follow when you draw these things. These Lewis structures. The first one is the one, as you can imagine, the magic number of 8 has been coming up a lot. And that basically is what is known as the octet rule. The octet rule is that everybody will continue to make bonds until they essentially have 8 valence electrons around them. Again, that's going to allow everybody to reach that noble gas configuration and be very stable. The one exception is sort of what we were talking about already a couple of times is hydrogen. Hydrogen does not need 8. It should never have 8. It should never have more than 2. And again, hydrogen only needs 2, as I just drew, to get itself over to the noble gas of helium. So hydrogen only needs 2 electrons, again, sometimes referred to as the duet rule, while everybody else will continue to make bonds until they get to that magic number of 8. So the octet rule is definitely something that you hear a lot when we talk about bonding and drawing these structures. Any questions on octet rule, the duet rule, which is hydrogen? And again, as I mentioned, that is essentially why hydrogen will never be on the inside, because it will have too many electrons. So hydrogen always has to be on the outside, and it really should, again, never have dots around it. Hydrogen, for some reason, people always like to do this move. I'm just gonna, because they're thinking everybody needs 8, hydrogen does not. Again, that gets you a big one of those. Yeah, so make sure you don't do that. Hydrogen, as I mentioned before, should only look really like that. Yeah, has 1 bond coming into it, which gives it 2 electrons. Any questions on that? Okay. So we sort of covered this earlier, but just to reiterate, there are different types of covalent bonds. The first one up there on the screen is our single bond. And again, you can represent the single bond 1 of 2 ways, like we talked about. If you want to do dots, you can do dots. Or again, if you want to do lines, it would be 1 line represents a single bond. And that essentially means that they are sharing a pair of electrons, or 2 total electrons, to get everybody to 8. Again, if you look at the fluorine and on each side, like we did earlier, they both have 8 valence electrons. Our double bond is represented again by 2 lines, which basically represents 4 electrons, or 2 pairs of electrons. And in certain cases, as we will see, Some guys need to share more electrons to get to 8, and that's what we see here with carbon. Again, the carbon down here actually needs to share 4 electrons on each side, and by doing so, it ends up with 4 on the left here and ends up with 4 electrons on the right, and that gives carbon 8 electrons, which is our magic number there for octet rule. And that also helps the oxygen on each side. There's 2 electrons there, 2 electrons there, and then also by sharing these 4 electrons here, that gives 4, 2, and 2, which gives it a grand total of 8 electrons as well. So in the case of carbon dioxide, they actually need to make a double bond on both sides in order to allow everybody to get to 8 electrons. And on triple bond here, same idea. A triple bond is actually the sharing of 2, 4, and 6 electrons, or 3 pairs of electrons. And again, represented by the dots are obviously a triple bond represented by the 3 lines. And here the nitrogen on the right, by sharing those 2, 4, 6, and 8 electrons plus its 2 electrons on the outside, gives us 6 and 2 gives us 8 electrons, as we see here. And same idea here. The guy on the left is going to be sharing those 6 electrons in the middle, along with the 2 on the outside, gives it 8 electrons, and that allows nitrogen to be happy. Both nitrogens on each side, they end up with 8 valence electrons each. And here with our C2H2, this carbon here sharing 1, 2, 4, 6, 8 electrons, giving it 8. Same thing on this carbon on the right-hand side. It has the same 2, 4, 6 electrons it's sharing, and one more over here gives us 8 electrons, and that gives each of those carbons 8. And as we see here, hydrogen does not need 8. It just needs those 2 that it has on both sides. And it's able to basically get to those 2 electrons and helium. So by sharing electrons here in this example on the bottom, both carbons were able to get to 8 electrons and become really stable, and both hydrogens were able to get to 2 electrons and also become very stable as well. Any questions on that there? And again, you technically can represent the bonding electrons with either dots or lines. A lot of times people will use lines for the bonding electrons, which again are those guys between 2 things that are involved in a bond. But again, you can represent them with dots if you like. But definitely the non-bonding electrons are always represented as pairs of dots. So these guys on the outside, if you have them, are always represented as pairs of dots to represent those non-bonding electrons. So since these guys are all basically sharing electrons, we want to determine, are these electrons going to be shared equally? Are they going to be shared sort of unequally, or how the sharing is occurring? And really the big thing that just helps us determine in a bond whether or not electrons are going to be shared equally or unequally is what's known as electronegativity. And we'll see it in just a sec, but that's basically the ability of an atom to bring electrons towards itself. So sort of your basic definition of electronegativity is the idea that an atom wants to bring electrons basically towards itself. And as we will also see, I think we might have talked about a little before when we talked about periodic trends, on the periodic table, electronegativity increases as you go up and to the right and decreases as you go down on the periodic table. And this is going to be really important to help us determine when we look at these electrons that are being shared between these two guys. Will they be shared equal or unequal? And depending on whether or not they are shared equally or unequal will determine what type of covalent bond that we would be dealing with. So this is where we're going to figure out the difference between a polar bond and a non-polar bond. And those are both covalent bonds. There are two different ways to describe a covalent bond in terms of how those electrons are being shared. So let's get into that then. So when we think about something, electronegativity does help us determine whether or not these electrons are going to be shared equally. It will also sort of help us determine whether or not they will be transferred, and you can kind of use electronegativity. We'll see some values in just a second, but essentially it will allow us to determine, if those electrons probably will become transferred and an ionic bond being formed versus a covalent bond. So if we look at a bond like we saw earlier, which is our H2, and basically because both of these elements here are hydrogen, they both will have the same electronegativity value, which means the hydrogen on the right will want the electrons just as the same as the hydrogen basically on the left. And that means that those electrons will be near each of those nucleuses and each of those hydrogens approximately the same sort of time period. And this creates basically equal sharing of those electrons. And definitely we would expect that because both these elements are the same. So they're both going to basically be pulling those electrons the exact same. So the hydrogen on the left is going to pull it towards itself. The hydrogen on the right will pull it towards itself. But the pull that those electrons will feel will be pretty much equal. And that creates a certain type of bond when we do get those equal sharing of electrons. That is basically what is known as a nonpolar covalent bond. And most people just call it just straight out just a nonpolar bond. Most people leave the covalent part off, but it really is a covalent bond. But most people will just call it a nonpolar bond. And so when somebody says basically this is a nonpolar bond, what that essentially means is the two atoms involved in that bond, they're essentially sharing those electrons equally. May not be perfectly equal, but it's some degree of what is considered equal sharing of electrons. Um, we'll talk about, there are kind of two types of nonpolar bonds as well. There's one where, in the case like what we see on the screen here, HH, they will share it pretty much perfectly equal with each other because they're both the exact same element, which means they have the exact same electronegativity. And that's was sometimes referred to as a pure covalent bond. A pure covalent bond is really a nonpolar bond. And sometimes people will classify them sometimes as a pure covalent bond because that's like perfect equal sharing of those electrons. And as we will see a little bit later on in a couple of slides, we can still call something a nonpolar bond without that perfect equal sharing of electrons, but it's still a little bit of sharing happening, equal sharing, but it's still considered basically a nonpolar bond. And we'll see sort of the difference between pure covalent and nonpolar, but they're both considered nonpolar equal sharing of electrons. But this is different when we do take something like HF. And if we take out one of those hydrogens and substitute it for a fluorine, and we make something like HF, if you remember where fluorine is on the periodic table, It is right there, upper right of the periodic table. Fluorine is the most electronegative element you can have, which means that fluorine, when it hooks up with hydrogen, fluorine's going to go, I would like the electrons to be near me. It's going to basically bring all those electrons over to its side, and not so much electrons happening at the hydrogen side. And this is going to result in unequal sharing of electrons. And that unequal sharing of electrons is basically what a polar covalent bond is, or just a polar bond, is that unequal sharing of electrons. So two types of covalent bonds. One is known as a nonpolar covalent bond, or just a nonpolar bond, and that is a result of what's considered equal sharing of electrons. Then we have a second type of covalent bond, which is a polar covalent bond, or just a polar bond, and that's a result of unequal sharing of electrons. So although it's unequal sharing of electrons, there's some aspect of sharing that's still happening. So that's why it's still considered a covalent bond. The electrons have not transferred from one element to the next. They're still hanging in there. They're still holding on. And again, that's why it's still considered a covalent bond. Any questions on the difference between polar and non-polar bond? Now, there is sort of a result that occurs because of this unequal sharing of electrons in something, say, like HF. Because the electrons are pretty much hanging out over by the fluorine more than they are the hydrogen, the result is this side is going to become more negative because it's got the electrons hanging out, while the side where the hydrogen is going to become more positive because the electrons are pretty much hanging out, over on this side. And what that creates on something like HF is what is referred to as a partial negative charge. And that's that little symbol there is the delta symbol. So a partial negative, and it creates a partially positive charge on the hydrogen in this case. And these are partial charges for what I was just talking about a second ago. They're partially negative and partially positive because although they're being shared unequally, they're still being shared here. Yeah. So we don't get a full transfer of electrons like we do in something like sodium chloride, where the sodium has transferred its electrons over to the chloride and it becomes fully positive charge, and the chloride becomes fully negative charge. And that's the ionic bond that we talked about in the last chapter. But here, because there's still some aspect of sharing that's going on, we call it a partial positive charge and a partial negative charge to represent that they're still being shared, those electrons. They are just being shared unequally. So another way, as we'll see on the next slide as well, I think is where it is, but just to preview it here. Another way that that could be represented is by an arrow. And this is what is sometimes referred to as a dipole arrow. Very badly drawn one there. And when we look at a dipole arrow, it always points to the more negative side. And the back part of the arrow usually has this little kind of almost plus symbol, points to the more positive side. So in HF here, the hydrogen is more positive, so it gets this back part of the arrow. It kind of makes a positive side. And then our fluorine here is more negative, so it points to the more negative side of that bond. So an ionic bond is the transfer of electrons from one element to the next, creating ions. So something becomes fully positive charged, something becomes fully negative charged. A nonpolar covalent bond is the sharing of electrons between two nonmetals, and that sharing is considered equal sharing of those electrons between the two elements. And then on the other end, we have a polar covalent bond, which is also between two nonmetals, also being shared, but the difference is it's being shared unequally. Any questions on any of those types? Okay. And I think that's what a little smear here is. So again, this kind of smear here is the electron density. Again, more electrons hanging out over on the fluorine side than obviously over on our hydrogen side. Again, you can represent that with this dipole arrow that's pointing to the more negative fluorine, and this side, which is the more positive hydrogen. And again, they create those partially positive and partially negative charges. Again, partially negative on our fluorine, partially positive charge there on our hydrogen. So another way you could kind of think of the difference between nonpolar covalent bond and a polar covalent bond is essentially in a polar bond, there's going to be a positive side and a negative side to that bond. And in a nonpolar, there's really no charge that occurs. It's kind of neutral if you want to think about it that way. There's no part of that bond that's more positive, no part that is more negative. Any questions on that? Okay. So when we think about sort of how to place those three types of bonding that we talked about, sort of at one end here, we have an ionic bond. And again, that's between a metal and a non-metal. We're going to have a transfer of electrons from the metal to the non-metal, and that's going to create a positive ion, which is our cation, and a negative ion, which is our anion. And here it's going to be held together by that electrostatic attraction. And again, the key here is no sharing of electrons. No sharing of electrons. So an example would be like what I put on the other screen, any type of ionic compound like sodium chloride. On the other end of the extreme, we have a nonpolar covalent bond. And that is between two nonmetals. And we have equal sharing of electrons. And that would be something like the H2 that we saw, the F2, again, our H2, they were going to share those electrons equally. And then in the middle here, we have a polar covalent bond. And in a polar covalent bond, what we got going on is also two nonmetals, also sharing of electrons, and it is unequal sharing of electrons. And that would be an example like what we got here. Yes, that's HF is an example of that. And again, because these electrons are not being shared equally, this polar covalent bond essentially will have a partially positive side and a partially negative side. But there's still some aspect of sharing happening there. They haven't fully transferred like we have in an ionic bond on the left, but there's some aspect of sharing. Any questions on the difference between those three types of bonds that cover from chapter 3 to chapter 4 here in terms of bonding? Okay. So how can we determine whether or not uh, these electrons in a covalent bond will be shared or equally or unequally? And it really is electronegativity that helps us do that. Electronegativity is basically based on two things that we talked about with trends. One is electron affinity. That's basically uh, something that likes electrons, wants to hang on to their electrons, and ionization energy, which is the energy needed to remove an electron. That's the energy. And again, when we look at the periodic table, in terms of those trends that we talked about, I think in chapter 2, as we go up and to the right, ionization energy increases. And as we go down, ionization energy will decrease. So up and to the right is our nonmetals. So they have very high ionization energy, which means they don't remove electrons. It takes a lot of energy to remove electrons. Extra L there. While to the left and down on the periodic table is our metals, which means they will pretty much have low ionization energy, which means it doesn't take a lot of energy to remove those electrons. So a guy by the name of Pauling basically came up with sort of a scale for electronegativity that helps you determine whether or not electrons will be shared equally. This scale of electronegativity goes from 0 to 4, 4 being the most electronegative, and we'll see it in just a second. While 0 being not so much, right? Pretty much not very electronegative at all. And we can use this scale and sort of some cutoffs to determine that if we take these two elements, two specific elements, and we put them together in a bond, would we expect that bond to be nonpolar, which means that we would expect those electrons to be shared equally, or would we expect that bond to be polar, which means those electrons would be shared unequally? And we can use this scale to sort of help us. And here's a version of that scale. Here's another version of that scale. And again, you can see the scale runs from 0 to 4. And you can see right here, upper right of the periodic table is our fluorine. It is the most electronegative. You can also see as you come down to the left and right, you have the smallest sort of version values. And basically, we could use these to help us determine whether or not something is going to be ionic, something is going to be polar, or something is going to be a nonpolar bond. And there's some general cutoffs. So if you take the delta En, which basically means the difference in electronegativity, running out of the screen. So difference in electronegativity is delta En. And if you take that difference in electronegativity, which basically just means you go to this table, you take the two elements and you subtract their values. If the difference is between 0 to 0.4, it is considered a nonpolar bond. And that basically means it's considered to be pretty much equal sharing of electrons. If you take the difference and it's above 0.4, so that's kind of like 0.5 to below 2, it is considered some type of polar bond, which means that the electrons again are going to be shared, but they are going to be shared unequally. And that's what's going to give us a partially positive side and a partially negative side. And if you do the difference, and typically it's above 2, that means it's going to give you an ionic bond. And again, these cutoffs are usually in most cases what it will be. It will work out that way okay. There are some exceptions, obviously, like anything, but those are the general cutoffs that we could use to determine whether or not a bond would be polar, nonpolar, or ionic. Now, this electronegativity table would obviously be provided for you if you needed it. You just need to know how to use it correctly. So, for example, How you could use it correctly is if we take a look at a bond that we saw earlier, our F2. If we look up on our electronegativity table, fluorine has a value of 4. This fluorine has a value of 4. So when we take the difference in electronegativity, it's basically 4 minus 4, which gives you 0. And 4 minus 4, which is 0, obviously would tell us that it is going to be a nonpolar bond. So we would expect these electrons to be shared equally. Now, if we take something like we also saw, I think, on the previous one, which is HF, hydrogen has a value of 2.1, and our fluorine has a value of 4. So when we take the difference in electronegativity, that's going to be 4 minus 2.1. Again, you can take the larger number minus the smaller number, and that would equal 1.9. Question is, where did I get 4? 4 is the electronegativity value for fluorine. So that's what this chart is right here. So that value right there on this chart is for 4 and for fluorine, and it has a value of 4. So what you're seeing on the screen is the electronegativity value chart, and each of the elements have a certain value associated with them, and that's where we get all these values for this. Just like the 2.1 there for the hydrogen came right there for our hydrogen. That's right here. Yeah. Other questions on that? Okay, so because the difference there is 1.9, it is actually still below 2. So this is considered a polar bond. Yeah? And a polar bond would mean, as we talked about before, we would expect these electrons not to be shared equally. So that creates a partially positive on the hydrogen, partially negative on the fluorine. And again, we can represent that with those charges, or you could just write the arrow above it to represent that it's a polar bond. We could also look at something like sodium chloride, which is a metal and a non-metal. And when we look at sodium here on the electronegativity table, it has a value of 0.9. And for its electronegativity, and we look at chlorine, which I scribbled on over here, is 3. So when we do the difference in electronegativity for this guy, we will get 3 minus 0.9. That gives us a value of 2.1. And again, that is above 2. And that would tell us that this is going to be an ionic bond. The electrons will be transferred from the sodium to the chlorine. Now, for the most part, to be truthfully honest with you, you pretty much don't need the electronegativity value when it comes to something that's an ionic bond. You pretty much, if you see a metal and a non-metal together, you're pretty much good to go, assuming that it's ionic. You don't actually need the electronegativity values. But the reason we do get those big differences is because non-metals are upper right on the periodic table, and our metals are kind of to the left and down. So when we put two of those guys together, we end up getting an ionic bond because there's a very big difference in the electronegativity values. As opposed to when we put two non-metals together, which is our covalent bonding. Non-metals are all in the same location here on the periodic table, which means they have very similar electronegativity values. And again, the best that they will do is essentially share the electrons. Any questions on that? Another very common bond that we come across is the carbon-hydrogen bond. If we look at the carbon-hydrogen bond, carbon has a value of 2.5, and hydrogen has a value of 2.1 in terms of its electronegativity. So when we do the difference in electronegativity, that's going to be 2.5 minus 2.1. That is going to give us our difference of 0.4. So this 0.4 difference would make carbon and hydrogen a nonpolar bond. And that really is why the cutoff is at 0.4. Carbon hydrogen is essentially a nonpolar bond. It's the basis of organic chemistry. And that's sort of why the cutoff actually goes to 0.4. Now, there is a difference, though, when we look at these two nonpolar bonds, right? This nonpolar bond, there is a difference of 0.4, not a big difference. This nonpolar bond, though, the difference is 0. And earlier I was talking about sometimes people call a covalent bond a pure covalent bond. And sometimes people would call this bond between the two fluorines a pure covalent bond, which again is still considered a nonpolar bond. But they would sometimes call it a pure covalent bond because the difference there in electronegativity is like perfectly 0. While up here, if we look at our carbon hydrogen bond, although it's still nonpolar, it would not be usually called a pure covalent bond because the sharing of electrons is not perfectly equal to 0. So there is some aspect here of unequal sharing. So when we look at something like this, there is some aspect of unequal sharing happening, and it's actually heading towards the carbon, but it's not to the level where people will consider it a polar bond. So even though it's still an aspect of unequal sharing because we do have a difference, that difference is so low it's still considered a nonpolar bond. So the difference between sort of a nonpolar bond and a pure covalent bond, or a nonpolar bond, which it also is a pure covalent bond, is sometimes thought of as having that perfect equal sharing of electrons, but still considered a nonpolar bond. But some people, again, will use that pure covalent for it. Up here with the carbon hydrogen, we would not use that pure covalent because although it's considered equal sharing of electrons, there's still some aspect of sharing that's happening, unequal sharing that's happening there. Any questions on that difference between pure covalent bond and nonpolar bond? And if you don't want to worry about the whole pure covalent bond, just call it a nonpolar bond. It's all good if the difference is 0. Now, what happens though if we put together, say, carbon and sulfur in a bond? These are two different elements that are coming together. So if we look at the electronegativity value for carbon, is 2.5. And if we look at the electronegativity value over here for our sulfur, it also is 2.5, which means if we take the difference in electronegativity, that is 2.5 minus 2.5. I'll do it without a calculator. I'm going to go with 0. And that 0 should tell us that it actually is going to be a nonpolar bond. So there's a couple of things about nonpolar. For sure, like it down here, or even in H2, these guys are all going to be nonpolar bonds because they have the same electronegativity. They're going to share the electrons equally with each other. Will create that nonpolar bond. But it is possible, as you see up here, that you could have two elements that are different but still share the same electronegativity values. And that is what is sometimes referred to as the diagonal rule. That, for example, carbon is higher up on the periodic table, but sulfur is further to the right. So they are diagonal of each other. So their differences cancel each other out. You could also see nitrogen higher on the periodic table, but chlorine is further to the right, even though it's lower. Also gets that diagonal relationship. So you see a lot of sort of diagonal relationships that can occur when you look at electronegativity and sort of the differences. And so you should be careful. Sometimes you can get, obviously, two different elements that share the same electronegativity value, and they're going to share those electrons equally and would be considered a nonpolar bond. But if you do have two of the same elements within a bond, they will definitely share those electrons equally, and it would be a nonpolar bond. Now, you also don't sometimes need I'll go back to this one so it's not so scribbly. You don't actually need these values if you're dealing with something that's in the same group or the same period on the periodic table. So if you did not have these values given to you, and you just had the periodic table like this without the values, and you were dealing with something like nitrogen and oxygen, because they're in the same period on the periodic table, oxygen is further to the right, which means it should be more electronegative, which means without even looking at these numbers, you will know that the nitrogen oxygen bond is going to be polar, because again, the oxygen is further to the right. You'll also be pretty safe to go, hey, the more negative side is the oxygen, the more positive side is the nitrogen. So if you're comparing two elements on the periodic table that's in the same row or period, the guy that's farther to the right will be more electronegative, and you actually don't even need the values to help you determine that. Same thing here if you're comparing somebody in the same group or column on the periodic table. So going up and down on that periodic table. So for example, if you were comparing these two guys, the oxygen and the sulfur, here oxygen is higher up on the periodic table, which means it should be more electronegative. And without even needing these numbers given to you, because they're in the same group, if you had something between oxygen and sulfur, for example, in a bond, you will know oxygen is further up in the group, which means it's more electronegative. So the arrows should be pointing to the oxygen. So if you find yourself trying to determine, are these things going to be polar or non-polar, you can actually use the general trend on the periodic table without having the numbers. If they're in the same period or if they're in the same group, you could just use that general trend to help you determine if something is going to be polar or non-polar. So just to finish up here for today, when we use electronegativity and these electronegativity values, it is used for really one purpose in the most cases. It is used for what is known as usually bond polarity. So when we talk about bond polarity, which is what we've been talking about here at the end with the electronegativity values, what we're talking about is simply when I take these two elements, are those electrons going to be shared equally? Are they going to be shared unequally? Or will they make an ionic bond? And basically, usually we use electronegativity oftentimes with just covalent bonds, because again, ionic bonds, you know, is metal and non-metal, so you can determine that just from that aspect. But we're basically just using these electronegativity values to go between these two elements when they share those electrons, these electrons in the middle, would they be shared equally or unequally? And that's not to be confused with something we're going to talk about later in this chapter, which is what is known as molecular polarity. So molecular polarity is something we'll talk about later in this chapter, probably on Monday at this point, obviously. But molecular polarity is something different. That's the entire molecule as a whole. But electronegativity values is what we use for individual bond polarity. Any questions on any of that stuff that we talked about today? So we should be kind of halfway-ish or a little bit more through chapter 4 at this point. Any questions on anything? Okay, so it seemed like most of you took the exam, which is good. I obviously haven't graded it. Again, I did put an announcement out yesterday, but just to remind you that I think it spits you out a grade when it's all said and done. Again, that grade that you saw in your exam may not be your final grade. I am going to go back through when I grade them. I haven't had an opportunity to do that yet, obviously. I'm going to go back through them and look at the work that you uploaded along with the answers that you inputted. And if you have an answer, as I look through it, that you inputted that technically is correct, but maybe the computer marked it wrong because of the way that you put it in, I will adjust your points obviously accordingly and stuff like that. So I am going to look at, all the answers that you submitted online and entered. And again, I'll try to catch all the ones that I feel were still corrected, but it just didn't like the way you kind of punched it in and stuff like that. And I'll adjust your score accordingly and obviously compare your the work that you uploaded. And again, even if you got the wrong answer but got some work on that page, that's correct. Again, I'll adjust your score. So my best guess is most of the scores that you see online will probably change, hopefully upwards, I'm assuming, in most cases. I don't think there will be a case, hopefully it'll go down, but in most cases it should obviously go up a little bit, maybe a lot, depending on sort of how the computer might have marked it right or wrong. So um, you will see some adjustments in those scores when I get a chance to grade the exams. Any questions on that? Okay. So that is, what is today? Wednesday. That's Wednesday. So that is it for the week for today. Uh, I'll end the lecture. Have a nice weekend. Um, and again, if you have lab today, make sure you go to your lab. Again, if you didn't get there because of the exam on Monday, I think she said you could come today virtually. So make sure that you do keep up with the lab. And I'll see everybody back here on Monday. Have a good weekend. Thank you, you too. Have a nice day. All right. Have a good day, everybody.